Bismillahirrahmanirrahim. This is our 13th lecture, and here we will see the energy considerations and rotational motions of the rigid objects. For this purpose, we have to assume some rigid object with its some pivot point through which axis of rotation passes. Let this is our rigid object, and point O is the pivot point of the object, and through this pivot point this axis is passing, and this axis is the axis of rotation of this rigid object. To discuss the energy variations in the rotational motion of the object, we have to assume some point on the object where a force, an external force, can be applied. So for the purpose, we take this point P, and this vector is representing the applied force. This vector is F vector, and it shows that at point P an external force is being applied. When a force is acting on this point P, then ultimately the rigid object will tend to rotate about its axis of rotation. So it will rotate in counterclockwise direction. Under this rotational motion, the point P is expected to dislocate from its initial position and acquire a new position. If this is the cycloid path along which the point P has traveled when the rigid object was supposed to rotate under the influence of this applied force, then we say that this arc length is so small that it can be taken as a straight line. Means it is small enough to be considered as a straight line. So we say that ds is a linear displacement between these 2 points, initial and final position of the point P, and if ds is a straight line, then we can also say that it will be equal to r d theta. Magnitude of this ds vector will be equal to r d theta, where d theta is the angular displacement, and this is an established fact as we have discussed in our previous lectures. ds equal to r d theta. Now our next task is to resolve this force into its rectangular components so that we can distinguish between its rectangular components, which of the component is involved in rotating the object, rigid object, and which component is not involved in this rotational motion of the object. So for this purpose we have to extend this line and say that this is our horizontal line, and as the vector f is positioned here, we say that this vector f is making an angle phi with the horizontal. So this angle is marked as phi. If angle is phi and vector is f, then we can find its rectangular components. Its horizontal component will be marked as f cosine of phi, and its vertical component will be marked as f sine of phi. We say that f cosine of phi is not involved in rotational motion because it is passing through the pivot point. In rotational motion, if any force is passing through a pivot point or axis of rotation, it is contributing nothing to the rotational motion. So f cosine of phi is not causing the rotational motion or displacement of point P from this point to this point. The only component of applied force involved in this phenomena of rotation and the displacing of point P from its initial to final position is f sine of phi. So f sine of phi will be taken into account while calculating the work done by the applied forces. So we say that if dw is the work done, then it can be calculated by dot product of two vectors. One is the force vector, other is the displacement vector. So f dot ds can be evaluated as f ds cosine of theta. Here we say that ds and f sine of phi both are parallel to each other. These are two parallel vectors. So theta will be equal to 0 and cosine of theta will be equal to 1. Hence we place the magnitudes of these vectors which are involved in doing work dw. So we place the magnitude of this force as f sine of phi and place the magnitude of this ds vector as ds, which is equal to rt theta. So dw will become equal to rf sine of phi t theta. We already know that rf sine of phi is equal to ta. Hence place the value of rf sine of phi over here and say that dw is equal to ta d theta. Now we are interested to find the power of this applied force. Means we want to know the capability of the applied force to do work with respect to time. Hence we will differentiate this expression with respect to time, and dw over dt will give p. P is power, and here d theta being a function of time will be differentiated with respect to time, and this vector will be equal to this ta omega, where omega is the angular speed. This is marked as equation number 2. P becomes equal to ta omega, and in translational motion we see that P is expressed as product of force and speed. Here we assume that force has been replaced by ta and P has been replaced by omega. This is the case of angular motion. The same thing is being discussed here, that in translational motion P equates Fv, and in translational motion we saw that P is equating ta omega. So these two equations are analogous. One is for translational motion, the other is for rotational motion. Another fact we have studied in the translational motion, that whenever there is a change in the kinetic energies of a system or of a body, and then this change in the kinetic energy appears in the form of work done by the system or on the system, and we expect the same result in our discussions of rotational motion. And for this purpose we start from the equation of rotational motion, which is taken as analogous equation to the Newton's second law of motion, and this equation is summation tau external is equal to I alpha. Here I is the moment of inertia and alpha is the angular magnitude of angular acceleration. So it will be equal to I d omega over dt. Omega is the angular speed. It can be rewritten as I d omega over d theta into d theta over dt, and d theta over dt can be replaced by omega. So this expression can further be rearranged as tau external d theta equal to I omega d omega. So tau external d theta is equal to I omega d omega, and in our discussions on the previous page we have mentioned that dw is equal to tau d theta. This expression is around our equation number 1 on previous page. So from here we take tau d theta equal to dw, so we claim that this side is also equal to dw. dw is equal to this. Now this is our concerned expression on which we will apply integral. So by integrating this part of the expression we can have w is equal to integral with limits omega I to omega f I omega d omega. This is our equation number 4. Now by integrating and application of limits we will be having half I omega f square minus half I omega I square, means this is the rotational kinetic energy at final moment. This is the rotational kinetic energy of the object at initial moment. So the difference in two kinetic energies at different positions appears in the form of work done by the system or on the system. So this expression 5 can be referred as work kinetic energy theorem for rotational motion, which will be analogous to the work kinetic energy theorem to in the translational motion, which we have earlier discussed. Here we are having an assignment, example 10.11 in the book Physics for Scientists and Engineers by Survey and Javed, 9th edition. Here we are going to deal with the problem of Atwood machine. In Atwood machine we are given two blocks of masses m1 and m2, which are interconnected with the help of a string, and the string is passing over a pulley, and the pulley is having a radius r, and its moment of inertia about its axis of rotation is I this is the pulley. Its radius is r. This pulley is attached with this bolt, and a string is passing over the pulley. One mass is attached with this, and the other is attached with this end. This mass is marked as M1, this mass is marked as M2. So its axis of rotation. This is the axis of rotation of the pulley, and it is having moment of inertia I about this axis. Some conditions are given here. The string does not slip on the pulley, and the system is released from rest. Initially the system is not moving, it is on rest, and when they are allowed to move, the blocks are allowed to move. When they are released, then by seeing here we can judge that mass M1 is smaller compared to mass M2, and mass M2 is having elevated position compared to that of M1. So ultimately it will descend and the mass M1 will ascend. Find the translational speeds of the blocks after block 2 descends through a distance h, and find the angular speed of the pulley at this time. When this block is ascending, the block 2 is descending, then pulley will be facilitating these ascending and descending movements of two blocks. So pulley will facilitate by rotational motion. Pulley will rotate about its axis of rotation. So for the purpose to discuss the energy variations in this motional activities, we have to fix the positions of the blocks, initial positions and final position. Let block M1 is initially at y1 position, and after ascending through height h, its position becomes y2. Similarly, so we say that y2 minus y1 is equal to h, and from this expression we will be having y1 minus y2 equal to minus h. Here y1 is the final position of block of mass m2, and y2 is the initial position of block with mass m2, and its opposite is here for block of mass m1. And we initially assume that the pulley, two blocks and the earth are treated as isolated systems, because these are the four objects which can interact through some forces with each other, and there is no external agent involved which can exert or experience some force with the linked with this system. So these four objects are making an isolated system. It's clear that when block 2 will descend, its potential energy will be decreased, and its converse will be for block of mass m1. Its potential energy will be increased because it is going to ascend through a height h. For energy considerations, we will have to refer to some law of energy. So we are taking law of conservation of energy, which states that total change in the kinetic energy plus total change in the potential energy of a system always gives zero change. This is our equation number 1, and we come to this point where the final kinetic energies and initial kinetic energies are expressed. In this parenthesis, we see that this is the final kinetic energy of block with mass m1. This is final kinetic energy of block with mass m2, and this is the rotational kinetic energy of the pulley, and its angular velocity is angular speed is omega f. Vf is the translational speed, which is common for block m1 and block m2. Here the initial moment the kinetic energy of all the three bodies, block 1, block 2 and pulley, as all three of them are at rest, so there will be no kinetic energy at initial moment. Final kinetic energies are expressed here. So this part refers to total change in the kinetic energy of the system. Now we are going to discuss the change in the potential energy, total change in the potential energy of the system. We have seen that block 1 was ascending from its height y1 to y2, and we have seen that y1 is its initial height, y2 is its final height, y1, y2, and we say that it is equal to h. So we can express the change in the potential energy of block 1 as m1g into y2 minus y1. y2 minus y1. m1g y2 will be referring to its final potential energy, and the term with y1 will be referring to the potential energy of the block 1 at initial stage. So y2 minus y1 is equal to h. So m1gh is describing the total change in the potential energy of block 1. And again, we have seen here that if y2 minus y1 is equal to h, then y1 minus y2 will be equal to minus h. So this is for block 2. Here block 2 gains its final position y1 and its initial position was y2. So to estimate the change in the potential energy of block 2, we will be having final potential energy minus initial potential energy, means m2g into y1 minus y2. y1 minus y2 will give minus h, and here plus m2g into y1 minus y2 will give minus h. This plus sign will be replaced with minus sign, and so m1gh minus m2gh will give the total change in the potential energy of the system. And by equation number 1, it is equated to 0. As rearranging all these terms. Here these are positive. On the right hand side, this term will become negative. This is negative here, it will be positive here. And so after simplification we have reached the translational speed, final translational speed Vf equal to this 2 into m2 minus m1 into gh over m1 plus m2 plus 1 over r square raised to power 1 by 2. So equation 3 gives the required translational speed of block m1, block of mass m1 and block of mass m2. This is the common speed for both the blocks. Now we have to find out the rotational speed omega f for the pulley using this expression, as we can link this translational speed with angular speed of the pulley by involving the radius of the pulley. So omega f is equal to Vf over r, and it can be written as 1 over r into 2 into this part m2 minus m1 gh over m1 plus m2 plus 1 over r square raised to power 1 by 2. So equation number 4 gives the required angular speed of the pulley, and this is our required result. Equation 3 and 4 are the required results for the outward machine problem. Thank you.